Hey everyone, and welcome to This Explainer. Today, we are demystifying machine translation, going all the way from the Tower of Babel to modern AI. We're going to embark on a really incredible journey today, diving into how we evolved from the messy, beautiful chaos of human language into the absolute mathematical elegance of modern machine translation. I mean, think about the last time you used an app on your phone to instantly translate a menu in a foreign country. Did you ever stop and wonder, how on earth does it actually do that? Well, by the end of this, you're going to know exactly why. We are breaking down the science, the algorithms, and the funny little quirks of human communication that make this whole technology possible.
Let's actually step back in time for a second. Peter Bruegel's famous 1563 painting, The Tower of Babel, highlights a really fundamental truth for us. Translation is not just some modern computational task, right? It is a profound, ancient human problem. It's all about bridging these deep divides between cultures and minds. From ancient scholars to modern software engineers, humanity has literally always struggled with the fact that we don't all speak the same language. So this quest to automate the process, it's really just our ongoing quest to bring the world a little closer together.
So let's dive into part 1, why translation is hard.
To understand how AI solves the problem, we first got to understand why a simple word-for-word swap just fails miserably. And it comes down to structural differences, what linguists call word order typology. Take English, for example. We use a subject-verb-object order. We'd say, he wrote a letter, with the verb right there in the middle. But in Japanese, the order is subject-object-verb. You'd essentially be saying, he a letter wrote, pushing the action all the way to the end. This is a stark contrast in the basic plumbing of the languages. It proves that a machine can't just read left to right and translate word by word. It actually has to perform massive structural reordering, holding on to information until the very end of a sentence just to make it grammatically correct in the target language.
And you know, languages also handle what's left unsaid completely differently. This is a concept called referential density. English is what we call a hot language. Basically, it spells everything out for you explicitly. We always use pronouns. We say, he went to the store, or it is raining. But cold languages like Japanese, Chinese, or Spanish are often pro-drop languages. They just routinely drop pronouns entirely because the context is already assumed by the speakers. So a machine can't just translate what is physically there on the page. It's forced to play detective, magically inferring who did what just so the English output actually makes sense.
And honestly, if grammar wasn't hard enough, vocabulary is an absolute minefield of lexical divergences. Let's say you want to translate the English word leg into French. There is no single answer. It changes completely based on the context. Are you talking about the leg of a journey? Well, that's étape. The leg of an animal? That's pas. What about the leg of a chair or a human? That's pied or jambe. The machine literally has to deeply understand the context of the entire sentence before it can even pick the right noun.
Okay, part 2, the encoder-decoder brain. Let's see how computer science tackles this.
Before our AI can start translating, it kind of has to learn how to read. Algorithms like WordPiece or Unigram don't actually look at whole words. Instead, they chop words up into much smaller, mathematically digestible pieces called subword tokens, which is brilliant, honestly, because it helps handle complex morphology, like prefixes and suffixes, and it allows the system to create a shared, efficient mathematical vocabulary across completely different languages. It deals seamlessly with both English words and Chinese characters using the same underlying logic.
Once we've got our tokens, we need to train the model. We do this using massive parallel corpora, aligning texts side by side. Think of the original French and the translated English versions of Antoine de Saint-Exupéry's The Little Prince. By applying some intense cost functions and dynamic programming, engineers carefully align the source and target texts sentence by sentence. This aligned data is essentially the lifeblood of the AI. It's the textbook from which it learns all those complex mathematical mappings between the languages.
And all of this groundwork builds into the actual brain of the machine, the encoder-decoder transformer architecture. Looking at the macro view, on the left, you have the encoder. Its job is to read and completely digest the entire input context, let's say an English sentence, and crush it down into a dense, intermediate mathematical representation. Then, it hands that context over to the decoder on the right, which uses it to generate the Spanish output words, one single token at a time.
But zooming into the micro view of these transformer blocks, we find the real secret sauce, the cross-attention layer. As the decoder is generating that Spanish sentence word by word, this layer acts like a flexible bridge. It allows the decoder to look back at the entire encoded English source text at any moment, paying literal attention to the most relevant English words required to generate the very next Spanish word.
This gracefully solves that nasty word reordering problem we were talking about earlier.
Moving right along to part 3, searching for the best path.
Once the architecture is set, we run into a major computational puzzle. How does the AI find the best translated sentence without checking every single mathematical possibility? Because look, if it uses a greedy approach where it just picks the highest probability word at step 1, it might easily paint itself into a grammatical corner and hit a total dead end by step 5. But if it tries to check every possible sentence combination, the universe would literally end before it finished translating a single paragraph. So how does it solve this?
The answer is a really elegant algorithm called beam search. Think of it like walking through a dark, branching labyrinth with an adjustable flashlight beam. Instead of lighting up just one single path, or trying to magically illuminate the entire maze all at once, the beam width illuminates a specific handful of the most promising paths simultaneously.
So let's say you have a beam width of 2. The algorithm calculates the ongoing probability of the paths step by step. It constantly drops the least likely branches and keeps only the top 2 options alive as it builds the sentence. It's this perfect compromise between speed and accuracy. It ensures the AI doesn't get trapped by a bad early word choice while remaining computationally fast enough to give you a translation on your phone in literal milliseconds.
Part 4. Translating low-resource languages. Now, moving beyond the mechanics, we absolutely have to address the global digital divide. What about the thousands of low-resource languages out there? The ones that don't have massive million-sentence parallel texts lying around. To bridge this gap, engineers use some really clever statistical tricks, things like back translation to create synthetic training data. But actually, statistics just aren't enough here. It is absolutely vital to use participatory design, bringing native speakers directly into the engineering process to curate and check the data. We have to ensure the translations aren't just mathematically viable, but actually culturally accurate and respectful. Finally, Part 5. How we grade AI. So, with these models generating millions of words a minute, how do we keep score? Human graders typically evaluate translations along 2 main dimensions: adequacy and fluency. Adequacy asks, did you capture the exact meaning of the source text? Fluency asks, does this actually sound like natural grammatical English or Spanish? And it's a remarkably delicate balance. Sometimes, a highly accurate, literal translation sounds completely robotic and unnatural. Conversely, a really beautiful, fluent sentence might entirely miss the original point.
Now, paying humans to grade every sentence is obviously way too slow, so computer scientists use automated proxies like the cry-F metric. It rapidly estimates quality by mathematically checking if the literal letters and spaces of the machine's output overlap with a gold standard human reference sentence. It's simple, it's fast, and it's surprisingly effective for everyday testing. But, as we know, language isn't just about exact character matches, right? What if the machine uses a perfect synonym that doesn't share any letters with the human reference? Well, for an even deeper evaluation, we use advanced neural methods like BERT-score. BERT-score moves beyond those exact string matches. It creates dense mathematical embeddings of the words to measure true semantic similarity. It knows that cold and freezing mean the same thing in context, even if they are spelled completely differently. This allows for a much more nuanced grade of the AI's actual performance. So, we've seen how these incredible models map our complex grammar and vocabulary into vectors, cross-attention layers, and search trees. But I want to leave you with a provocative thought today. As AI models seamlessly bridge our ancient linguistic divides, will they preserve the beautiful, messy quirks of our hot and cold languages? Or will they inevitably flatten human culture into pure, homogenized math? It is definitely something to keep in mind the very next time you tap Translate on your screen. Thank you so much for joining me in this explainer. Keep learning, and I'll catch you next time.